Seismograph stations on every continent recorded a signal no algorithm could classify. 68 scientists from 40 institutions spent over a year trying to identify what caused it. A mountainside collapsed into the ocean at 42 meters per second because the glacier holding it in place had melted away from the inside. The wave, trapped in a narrow fjord, sloshed back and forth every 92 seconds for more than a week, ringing the earth like a bell at a frequency never recorded from any glacial source. Across the Atlantic, Greenland's fastest glacier is now confirmed to be in what researchers call an unstoppable phase of marine ice sheet instability. A 2026 study modeled building a 150-meter underwater wall to block the warm water eating it from below. The conclusion was that nothing would stop it. And on the opposite end of the planet, satellites just detected the ice shelf holding back Antarctica's Thwaites Glacier, fracturing and pulling away from its last stabilizing anchor. Both poles failing at the same time. But here is the detail buried in the data that nobody is talking about. The tsunami warning network that protects the North Atlantic was built to detect earthquake-generated waves. It was never designed for what glaciers can do. Monitoring buoy coverage along Greenland's western coastline is 1/5 of the coverage in the Pacific. Professor Herman Fritz at Georgia Tech, who has spent over a decade studying glacial tsunamis, put it simply. This tsunami arrived very fast, within minutes. That basically leaves no time for warnings. People have to self-evacuate. The communities closest to Greenland's glaciers would have roughly 5 minutes before a wave arrives. Evacuation models for those same communities require a minimum of 20 minutes. That 15-minute gap is not a planning problem. It is a death sentence written into the infrastructure, and no one has funded the fix. September 16, 2023, 12:35 Coordinated Universal Time. A peak called Vid Stovhorn perched 1,200 meters above Dixon Fjord in eastern Greenland, let go. 25 million cubic meters of rock and ice ripped down the mountainside and hit the water at highway speed. The fjord detonated. The initial wave climbed 200 meters up the opposing wall. Subsequent surges reached 110 meters. Run-up was still measurable 100 kilometers away. Within minutes, hydrophone arrays originally built to monitor Cold War nuclear tests picked up the acoustic signature across a listening range of over 2,000 miles. Seismographs in Iceland, Norway, and the northeastern United States time-stamped the event with extraordinary precision. But the instruments did not record an earthquake. They did not record a volcanic event. They recorded something that had never been formally documented at this scale. A hybrid signature, part mechanical fracture, part hydrodynamic impact, a seismic fingerprint without a category. Christian Svenevig, a geologist at the Geological Survey of Denmark and Greenland, led the investigation. His words capture the confusion. He said that when they set out on this scientific adventure, everybody was puzzled and no one had the faintest idea what caused this signal. It took a team spanning 40 institutions to determine that the wave, trapped inside the narrow fjord, had created a standing wave, a seiche, that oscillated every 92 seconds for 9 days without stopping. The energy had nowhere to go. The fjord was a bell, and the mountain that collapsed into it had been held in place by a glacier that no longer existed. Here's what that means. The glacier did not just melt, it performed a structural function. It held the mountainside together the way a retaining wall holds back Earth. When the ice disappeared, the rock had nothing bracing it. The collapse was not a random geological accident. It was a predictable consequence of ice loss that no monitoring system was watching for. Now zoom out. Greenland's west coast, Disco Bay, the Ilulissat Ice Fjord, a UNESCO World Heritage Site where 4,500 people live at the mouth of the drainage channel for the single fastest moving glacier on the island. Jakobshavn glacier, known to researchers as seismic, drains 6.5% of the entire Greenland ice sheet. Every year, it produces roughly 35 billion tons of icebergs that pass through the fjord and into the open Atlantic. In 1985, the glacier's terminus moved at 6,700 meters per year. By 2003, that velocity had nearly doubled to 12,600 meters per year. One glacier, singularly responsible for 4% of all sea level rise in the 21st century. And here is the part that is not making headlines. In February 2026, researchers at Kiel University published a 115-year reconstruction of freshwater discharge flowing from the ice sheet into Disco Bay. What they found was not a gradual increase. It was a regime change. Meltwater runoff shifted into sharp, nonlinear acceleration starting in the early 2000s. By 2007, the volume of freshwater entering the ocean permanently exceeded the range of natural variability observed across the entire 20th century. It has never come back down. Their conclusion was direct. This provides independent evidence for a nonlinear accelerated response and warns that a tipping point in glacial mass balance might soon be reached. To understand why that tipping point terrifies glaciologists, you have to understand what is happening beneath the ice where no satellite can see. Warm Atlantic water, pushed north by shifting ocean circulation patterns, is tunneling beneath Jakobshaven's submerged base. This process, submarine melting, does not chip away at the glacier from the front. It carves out hidden cavities from the bottom up. The surface looks solid. Underneath, the ice is hollow. And every degree of ocean warming at that interface doubles the melt rate. But that is only half the mechanism. Jakobshaven sits on what glaciologists call a retrograde bed slope. The ground beneath the glacier does not rise as you move inland. It drops, deeper and deeper. That geometry creates a trap. As the ice front retreats into deeper water, more of the glacier face is exposed to warm ocean. More melting, faster retreat, which exposes more ice in even deeper water. The loop feeds itself. A separate study in 2025 modeled the most aggressive intervention imaginable, building a physical barrier 150 meters tall across the fjord mouth to block the warm water entirely. The finding was devastating. It would not matter. The glacier has already entered an unstoppable phase of marine ice sheet instability. The geometry of the ocean floor has made the retreat self-reinforcing. Then came the discovery that rewrites the timeline. In November 2025, researchers using a 10-kilometer fiber optic cable deployed along a glacier front discovered that every calving event, every chunk of ice that breaks off and crashes into the ocean, generates massive hidden waves beneath the surface. Not surface tsunamis, internal tsunamis. Underwater waves moving between ocean density layers, reaching heights comparable to skyscrapers, and persisting long after the surface goes calm. These waves violently mix warm deep water upward toward the ice face, accelerating melt far beyond what any previous model accounted for. The glacier is not just retreating, it is feeding the process that destroys it every time a piece breaks off. Now consider the scale. The Greenland ice sheet loses 264 billion tons of ice per year, 9 billion liters every single hour. That is 3,600 Olympic swimming pools per hour. 24 hours a day for the 29th consecutive year. Over 5 trillion tons gone since 2002. And the ice that remains holds enough frozen water that if it melted entirely, global sea levels would rise by 7 meters, 23 feet. That number redraws every coastline on Earth. New York's Lower Manhattan sits less than 10 feet above current sea level. Miami's average elevation is 6 feet. Bangkok, home to over 10 million people, averages 1.5 meters. These are not projections for a distant century. Glaciologist Jason Box at the Geological Survey of Denmark and Greenland has published research showing that Greenland's ice is already committed to at least 274 millimeters of sea level rise, roughly 10.7 inches, regardless of what humanity does next. That loss is locked in. The question is only how much more gets added on top. And while Greenland accelerates, the same process is unfolding 15,000 kilometers away. Antarctica's Thwaites Glacier, the one scientists call the Doomsday Glacier, is responsible for 4% of the annual global sea level rise on its own. In late 2025, satellite data revealed its eastern ice shelf is progressively fracturing, pulling away from the underwater ridge that has been its last stabilizing anchor. Researchers from the UK and Korea drilled 1 kilometer through the ice in early 2026 to directly measure how fast warm water is eating it from below. The same warm water, the same mechanism, both poles caught in the same trap. The warning systems that are supposed to protect people from what these glaciers can do were never built for this threat. The Global Tsunami Early Warning Network, constructed after the 2004 Indian Ocean disaster that killed over 200,000 people, is genuinely impressive for earthquake-generated waves. Thousands of seismic stations, hundreds of deep ocean pressure sensors, satellite uplinks spanning dozens of countries. But glacial tsunamis behave differently. They originate from a point source, a concentrated impact zone, where ice meets water, generating shorter, more chaotic wave patterns that pressure sensors frequently misread or underreport. The monitoring gap along Greenland's western coast, is not a secret. Buoy density there is roughly 1/5 of the coverage maintained in the Pacific warning zone. Communities within 60 miles of a potential collapse have a realistic warning window of 8 to 14 minutes. Evacuation modeling for those same communities assumes a minimum of 20 minutes. In Ilulissat, where 4,500 people live at the mouth of the fjord that drains Jakobshavn, the fishing boats go out every morning because the fish are still there and families still need to eat. The ice fjord behind them is a UNESCO treasure and a tourist destination. It is also the barrel of a loaded mechanism that 2026 research says cannot be stopped, only measured as it accelerates. The question glaciologists cannot yet answer is which section of Greenland's ice reaches its breaking point next. The question the rest of us need to answer is whether anyone will hear it when it does. The meltwater is still accelerating, the internal waves are still churning, the bed slope is still dropping, and the warning system designed to protect the North Atlantic is still listening for the wrong kind of wave.